So thank you, and I'm happy to be here. Thanks for inviting me to present our work on quantum transport and discrete time crystals. This work I did with Yoni Dubey in Bengaluru University, and the work will be based on these two papers. So as I'm talking about discrete time crystals, first let me give a layman view of what is discrete time crystals. So these are periodically driven quantum many-body systems which has subharmonic response. These subharmonic response are indefinitely stable and robust against perturbation. So if I drive the system with some period t, the response should have a period which is more than t. And one criteria to look for if there is a subharmonic response is to look for the autocorrelation which are initially normalized. And regarding the robustness against perturbation, it depends on what kind of perturbation I am giving. So with that, so let me emphasize that this is a defining character of one of the most important defining character of discrete time crystals. And what I'm going to convey you that in a simple message that in a transport setup, current through electrodes can show the signatures of discrete time crystals. So by transport setup, what I mean is that I have a bunch of lattice sites where each site is being driven periodically with some period, and then I connect that system with two reservoirs. So from the left reservoir, I just inject particle, and from right reservoir, I extract it, and I complete the circuit, and I see current through the circuit, and then from that current, I can directly infer that okay, I have a DTC. So to motivate, so let me first go through some selected experiments just to show you how there are several experiments just to show you the paradigms of discrete time crystal. So if in a closed system, one paradigm is if you have a many body localized phase, then you have a discrete time crystal, and there is a subharmonic frequency and period doubling. So here the blue line, it corresponds to the MBL phase, and the system is a chain of carbon atoms near an NV center. So now if you are moving away from many body localized states, your time crystal will decay, and far away it will have multiple frequencies. So there is another paradigm which is called pre-thermal discrete time crystals, where you have a long range interacting system such as an ion traps quantum simulator, and you drive the system really fast, like very high frequency. And in this way, you just separate out a few time scales, like one is a thermalization time scale, one other is a pre-thermalization time scale. So in between that, you have a sustained oscillation, and the oscillation will eventually decay, but the decay time will increase as you increase the driving frequency. It's actually what is happening, as far as I understand, is that the system is not following the driving frequency, and that's why you have this pre-thermalization. But these are all the story in the closed system. So the point is, in closed system, if you continuously drive a system, you generate heat, and your system will eventually heat up to zero oscillation. So to counter these pre-thermal and MBL phase, MBL time crystal has been proposed. The point is that one just hinders or delay the thermalization, and another is just stops the energy from spreading across the system. Now, another aspect is open system. Here, if you give energy to the system, since your system is open, it just dissipates to the environment. In that way, also you can stabilize a discrete time crystal. So this is an experiment where they have a cavity, they have a rubidium collection of rubidium atoms in a cavity, and they're pumping from outside, and they have this cavity field. Now, they prepare the system in a Bose-Einstein condensate, and above certain critical pumping field, they start having VEC to density wave transition. And once they have a density wave transition, they basically oscillate between two different type of density waves, like two different checkerboard patterns. Now, this is their driving protocol, and this is the time crystal oscillation. Now, here is an interesting feature. So the time crystal is seen between the relative phase, in the relative phase between pump and cavity field. Now, in their system, as long as they have a cavity field, finite cavity field, they have what is called a mean field character of the Hamiltonian or the system. So you can clearly see that as the cavity field decays, you lose the time crystal although the amplitude of the oscillation remains, you just lose the frequency. So this is a signature that once you go away from the mean field limit, you lose the time crystal in the frequency. A similar study has been done on a car nonlinear optical microcavity, and then they also find some similar thing. So my point in these slides is that the state of the art is only optical detection. So you just have optical means of looking at time crystals. And I asked that, what about transport? So let me find an analogy, the situation. So I have a bunch of kids. Kids are like quantum particles. So they are there playing. And then they are locally creating some time crystals. Now, optical detection is something like this. You send up a drone and look at the drone footage and say, oh, haha, here is my TC. And I don't have the money to buy drone. I just do what? I regularly clean my pool. So I just add a smooth flow of water, and kids are still playing. They don't know there is a smooth flow of water. So the time crystal will propagate through, and the mom is sitting far away from the kids. She can just see and look at the flow and say, oh, I can see the kids are playing TC game. So this is the kind of analogy that I'm imagining. So to see this, so first I have to look at what to expect from the transport setup. So to do this, I just work in the Lindblad equation premise. So Lindblad equation says that I have a system inside some surroundings. The system's density matrix will evolve in time following this equation. This equation has a coherent part and a dissipator part. The dissipator part contains a collection of jump operators or Lindblad operators. These Lindblad operators encodes what the system, what the surrounding is doing with the system. So basically, for example, if I have a boundary drive like the electrodes or the leads I showed you, the leads will create particle to the system, and one end it will also extract particle from the system. So this is how it works. So in my case, I will work only with the Markovian limit, and my Hamiltonian is periodic. Therefore, all the periodicity in my Lindblad or Liouvillean is coming from the Hamiltonian. In the operator form, the equation of motion looks like this. Now, this is what we'll be analyzing in the next slide. So now let's see what to look for if I want to have a time crystal. So I have a Liouvillean which is time periodic. What I will look at is one period time evolution map or Floquet map. This looks like a time ordered exponential of the Liouvillean superoperator. The superoperator means that I have a density matrix which has the dimension of the Hamiltonian. I just make the density matrix a vector and extend that the Liouvillean accordingly. And then for all the basis states, I time evolve the Liouvillean, I mean this thing, to get after one period one Floquet map or the time evolution map. Then I diagonalize it and plot the real and imaginary part of the one period Floquet map. So as you can see, there is one state which is at eigenvalue 1. All the rest of the states are decaying. This state is called Floquet state, Floquet steady state. And correspondingly, I don't have any phase over there. It's just 1 plus 0i. Now, what will happen if I have an underlying discrete time crystal? How do I see it? So if I now diagonalize a one period Floquet map, apart from this Floquet steady state, I see other states which appear on the unit circle, but having a phase. So the magnitude of the eigenvalue would be 1, but it will have a phase. Now they appear in pair. So here, the phase is like 2 pi over n. I mean, the n might not be integer, it might be fraction. If you have a fractional n, then you call it's a discrete time quasi-crystal. Now, the density matrix will have a nt periodicity, while the Liouvillean will have a t periodicity. And this is how I will diagnose a discrete time crystal from one period Floquet map. What is the mechanism by having a discrete time crystal? So I showed you the equation of motion for the operators. So my Hamiltonian is periodically driven. I have a dissipator. Then I try to find out a frame where Hamiltonian becomes effectively static. And if I find such a good way of having such a frame, then my equation of motion is is time independent, by my right-hand part is time independent. And the mechanism is something called dynamical symmetry. This is a brainchild of Borislav, who is sitting there. So it says that Hamiltonian, and there is an operator called dynamical symmetry operator, which satisfy eigenoperator condition with the Hamiltonian, and the dissipator part is 0 for this particular operator. In that case, I will have a discrete time crystal seen in the dynamical symmetry operator. What is actually happening is that dissipator is separating the full Hilbert space into separate disjoint subsectors. So each subsector will oscillate with the frequency omega, and this dynamical symmetry operator will act as a dark Hamiltonian, which will induce some coherence between two different subsectors, and that coherence has a value of lambda, which will be seen as a response. So the role of the dissipator is to have this kind of a separation. So this dynamical symmetry is such a separation of Hilbert space or such kind of thing occurs like more generally in systems such as quantum many-body scar and systems like that. And in that sense, it will be like something like an eigenoperator thermalization, which Borislav will talk about in his lectures. In my case, I want to now see what happens to the transport. So given I have such a mechanism of DTC, I don't want to send my drones. I just want to see it in transport, that means on the water flow. So I add leads, and the kind of systems I will imagine, I'll show you shortly, these leads are naturally there. They need that to implement their setup itself. So in that case, particles will flow in to the two different sectors and flow out, and while going out, it just captures the underlying coherence. So in that case, what we must have is that apart from the eigenoperator with respect to the Hamiltonian, I also need to have an eigenoperator with respect to dissipator, and this lambda and gamma, they should not depend on each other. And in that case, I'll have this decaying envelope, but the frequency will not be hampered, as I will show, and I will see oscillations in the current under this kind of a mechanism. So to show it, so let me show you the model and the setup. So I have a Fermi-Hubbard model. I drive it externally. I have a local Z-man type circularly polarized drive. I have hopping of electrons from one side to another. I have on-site interaction. I have nearest neighbor interaction. And I also have something called spin agnostic dephasing. It means that it's measuring number of particles at a rate of square root of gamma, total number of upspin and downspin electrons at a rate square root of gamma at each site. Now I add electrodes. So from left I inject, and from right I only extract. So this is a condition corresponds to an infinite bias condition. Now with this model, let me now analyze the one period Floquet map for various values of gamma, my system lead coupling, and which is usually tunable. So here I plot for various values of gamma, the one period Floquet map, the way I explained you, the way I got it. Now, this is the real part and this is the imaginary part. And if I have a gamma equals to 0, that means no transport. I have this as my DTC eigenvalue. Now, if I start adding transport, I see that there is a real part coming in, and that real part is not, that real part has only effect to shift these time crystal eigenvalues along a ray. So importantly, we have omega equals to all other energy scales of the system. So the role of the system lead coupling is to shift the eigenvalues along a ray. And in this way, what we can see is that although the amplitude of the signal reduces with increasing system lead coupling, but the frequency remains intact. So this will help us seeing time crystals in the current. And how? So this is the kind of picture I have. So I'm plotting here spin current. Spin current is the difference between the upspin current and downspin current. So I think I forgot to mention the kind of setup I am imagining is on a quantum dot array. So here in quantum dot array, we have naturally they implement these source and drain. So here I plot spin current as a function of time for say 100 driving periods. So if I have a weak system lead coupling, I see sustained oscillation, which is expected, and I have a frequency at 5/3 omega. Now, if I increase the system lead coupling, some intermediate values, I see the oscillation amplitude decays, but I still see a sustained oscillation in, say, these long time periods, long time scale. So here also I have the frequency 5/3 omega, but now I am increasing the system lead coupling to something like beyond I expect using Lindblad equation, such as like almost 1/50th of the frequency or the energy scales of the system. Here also I see the frequency remains there, but now we have lots of broadenings because of the amplitude decay. What is happening is that I get this frequency from two components. One is the amplitude, another is amplitude of the external drive, and another is the frequency of the external drive. And as you notice, the spin current provides a signature of the coherence between the system symmetry subsector, and it directly reflects the coherence, and the amplitude remains locked. And this is, I find, beneficial for looking at a time crystal using transport. But you may argue that this is 5/3, so it's higher harmonics. It's not subharmonic. So let me now show you where actually the time crystal appears. The time crystal appears in SY. SY is so in my case, I'm working with Fermi-Hubbard model. In Fermi-Hubbard model, the dynamical symmetry operator is the total spin raising operator. So real or imaginary part of that total spin raising operator at any site will oscillate, and that will show me the time crystal. So although I'm getting a higher harmonics in the current, the time crystal appears in SY. As you can see, this is the SY for gamma equals to 10⁻⁻5 omega. So the order of gammas are same as here and here. So this is the small gamma, and I have a frequency to 2/3, which is the coherence modulo omega. So in my choice of parameter, it's a rational fraction. So I get a period time DTC period, which is P times T. And if I increase the amplitude of the system lead coupling, and I get the same frequency, and then the entire feature remains the same. One thing worth noticing is that here I have a synchronization. So I plot 3 different sites, and all 3 sites are oscillating in synchronization, but they did not start with in synchronization. So the role of gamma is to bring, the gamma means the dephasing, is to bring the synchronization. And the role of a boundary drive is to drive a current through the system. Now let me connect why I have a 5/3 in the current and 2/3 in time crystal. So to connect that, I look at the Fourier transform, and I see there is a component at 2/3, there is a component at omega. So clearly, this combination is drawn here. These two matches with each other. This is my analytical form here, and this is what I get from numerics. As you can see, the SY has 5/3 omega and times sine of omega t. Similarly, I can have an SX, which also have a 5/3 omega component and omega t/3. Now, given that for very small gamma, I must have this property to be constant. As you can see, the SZ oscillates. I should oscillate with 5/3 omega. And this is what was happening here. Now, Having said that, I showed you that I have to look for the spin currents. Now, looking at spin current is difficult in the sense I have to then tune my leads in a quantum dot setup to really filter up spin and down spin and then look at the spin current. So let's implement the whole thing in a charge measurable setup. So the symmetry, underlying symmetry in my Hamiltonian is SU2. So I want to implement the SU2 symmetry system in a array kind of structure. So now here is my imagination. So I have a chain of dots. Each dot contains spinless fermions, and their energy levels can be changed by some gate thing. And then electrons can hop from one dot to another. They can have on-site and nearest neighbor interactions. One non-trivial thing to implement is the interchain hopping now needs to be periodic. So if I can implement this interchain hopping to be periodic, then my setup can show, given a periodic omega periodic drive, that 5/3 omega in current. Now this imagination is not far from reality, although I did not know it earlier. So recently I figured out that there is an experiment implementing SSH model on a quantum dot array setup. And as you can see, in their setup is architecture-wise quite similar to a ladder structure. And they also have a source drain. So only non-trivial part would be to have interchain hopping periodic and to implement the spin agnostic, in this case, this chain-wise, ladder-wise dephasing. So if that can be implemented, then the discrete time crystal is seen in charge current. So I drive the system and I see charge current oscillating in time, giving me a 5/3 omega frequency. And this time I don't need to separate out upspin and downspin contributions. But the underlying DTC is actually in a different operator. That operator is the interchain tunneling operator. Either real part or imaginary part will show these 2/3 omega oscillations. So therefore, so now the bottom line is that charge current shows discrete time crystal behavior. Now, one more thing we can do with this kind of a ladder setup is that we can use gates to increase or decrease the on-site energy. So there is another tuning parameter, which is the on-site energies. So depending on the difference of on-site energies, I can now tune between time crystal and a Floquet response. Now, question is it really a Floquet response, or is it really a Floquet steady state? That's what I am going to answer now. So when my delta epsilon is 0 or some value that gives me lambda by omega as a rational fraction, I get a DTC response. And at a value when delta omega is exactly equals to the magnitude of the hopping, interchain hopping, this hopping, then I get lambda by omega as an integer. That means my DTC period is actually exactly same as the Floquet response. Now if I deviate from this point, I again start seeing subharmonic response. So actually what is happening, you can see it in current. I start from a lambda where delta epsilon, where I have DTC response, I change. So it's seen in the current. And as you can see, it's seen in the Fourier transform. So now once I change it to a value, which is like equal to the T hopping, interchain hopping, you can see now I have a response, which is Floquet response. Now, if I change it back, I get back to the DTC response once again. What is happening here? A DTC state is moving along the unit circle, and it just becomes degenerate with the Floquet steady state. And once I change the parameter again, it starts moving. So it's just a degenerate, but the DTC state is really orthogonal to the Floquet steady state. So I was expecting that once it goes there, it will remain there, but it's not actually because of the orthogonality between them. So with this, so let me now summarize. What I showed you is that that there can be an electrically tunable quantum dot array setup where we can implement a way to measure time crystal in current. And we can have both in spin polarized and charge current. And the amplitude decays, but the frequency remains same. This is due to our weak local Floquet dynamical symmetry. And I forgot to mention why it is weak and local. So the weak because your amplitude is decaying, and local because you are now having the dynamical symmetry not with the extensive spin operator, but the operators that are situated on the left, near the left and the right lead. This is why we named it a weak local Floquet dynamical symmetry operator. So basically, what it does is that it adds an extra eigenoperator condition on top of the eigenoperator condition you have had in the Hamiltonian, and robust. This is robust against quenching of the system parameters. This I end.
Thank you. Let's thank the speaker. Questions?
Floquet map diagram, you might have a finite number of spins, right? And you are studying it as a like the decay rate dependence on the real part of the eigenvalues, right?
Yes.
What is the effect of the system size scaling on that?
There is no effect on the system size scaling because this is analytical. This is just a representative kind of to support the analytics. It's analytically provable.
So if I take like a finite number of spins, like 2 or 3 spins, that will still exist?
Yes, yes.
Okay, correct me if I'm wrong, because like I think the many body correlation stabilize this discrete time crystals phases, right?
This discrete time crystal is stabilized by the dephasing. Actually, your dephasing creates a disjoint subsectors, and that's where the discrete time crystal is coming.
And one more question on that is that when you have local dephasing, can you still conserve the total spin that I think you have shown on one of the slides?
So the dephasing has to be spin agnostic. That means it has to be an up plus and down. Otherwise, you cannot.
I think
this dephasing conserve the conserve the number, particle number.
Okay. Yeah.
Okay. Abhishek, the question.
It's a very basic question. I mean, so these 2 extra eigenvalues that you get, and does this happen in the kind of thermodynamic limit, or it's finite?
Irrespective of taking thermodynamics.
It happens in a finite system.
It's just like it's an analytical condition. In order to show it through Floquet map, I had to consider finite size. But the condition, why is it coming, is because of why is it coming is because of this equation. So if you make gamma 0, then you will always have this kind of a irrespective of the system size. And even with gamma, it's just adding an extra decay, and this decay is actually helping me to see the current. With 0 gamma, I cannot have a current, right? So
no, but then why is it a crystal? Because crystals normally you think like it should be in the.
So analytically, it's just in the any n, like, and it's valid also in n tends to infinity limit. I just cannot have like a way to show it here. Like, in order to have the entire spectrum, I have to have finite number of particles.
So I guess the question is, suppose I just had one dot coupled to two bars.
There is no.
How many minimum dots would you need?
Two at least. Two. And this was the question from the referee also.
Yeah. So you need two for the operator algebra to work.
Yes.
Any other questions? Yeah.
Yes.
that's basically the steady state, right? You must have it because there is a steady state
Yes.
somewhere. And then you say the oscillations come because there is like well, the time crystal, because there are 3 points that are somehow
Yeah, this
symmetric.
this doesn't have a phase, so it's kind of will follow the drive.
Yeah,
It will respond same as omega,
right.
and this has an extra phase.
Right.
So you have to have that extra that because of that extra phase you get these extra periodics.
Right. So my question was, if I understood correctly the story, at least in the transverse shieldizing model, it is actually not just a property of one eigenvalue, but all eigenvalue will have, say, a pair exactly.
Yeah, there is a pair.
No, I mean, so I'm saying, let's take another dot. Will it also have a partner? Or is it only the steady state that has a partner?
Okay, so this is this specific value is because of my parameter choice.
Yeah, no, I understand.
So-
But let's
so-
say you take a point in the middle, not on the edge of the spectrum, not the steady, not just in the middle, not any of those dots you have.
So you're saying they have a partner or not? I think yes. There are. I mean, is it like?
Yeah, that was the question. Yeah, if every point will have like two partners.
Kind of,
or-
yes.
Yeah, you think so? Okay, thanks.
No, but then this point no. This point cannot have two partners, right? This is a unique state. Apart from that, like these, I guess all of them have partners. Because these has phase, so they come in pairs. But this doesn't have a phase. Question is what? Okay.
I just wanted to say, but I think it's clear, they must come in pairs because of hermeticity preservation of the map, yeah? This is guaranteed. And then now I understood that you're asking something else, but
Any other questions? If not, let's thank the speaker.
Thank you.